Okay, we're moving right along. We just talked about combination and decomposition reactions in the last video. Now we're going to be talking about single and double replacement reactions here. We're going to start with single replacement reactions though first. So a single replacement reaction is one element appears to replace another in a compound. Okay, so this is kind of the example here where this element is replacing this element. So A is replacing B in the formula here. Okay, so now you have A with X and B is kicked out. Okay, whereas you started with B with X and A is kicked out. Okay, so these guys are switching places. Okay, that's the key here. That's a single replacement reaction. So B is with its partner and A comes around and wants to kick B out, all right, and B with X. That's what's going on here for single replacement reactions, okay? So let's do some examples. So a magnesium wire is placed in a solution of nickel nitrate. Write an equation for this reaction. Okay, so here we go. So it's a single replacement reaction. So the reason I'm realizing that is because magnesium, right, is just an element by itself. So we have magnesium, and I'm going to write the general structure for a single replacement reaction up here. Okay, so magnesium plus nickel nitrate. Okay, now remember nickel has a +2 charge. Okay, so that's the formula for nickel nitrate. I'll just write it off to the side here. So we have nickel with a 2+ charge, nitrate with a 1- charge. So when you crisscross the charges, okay, you get nickel. Let me move my little screen there, nitrate. Okay, so that's nickel nitrate. So what is going to go on here? So again, if I just write it right under here, we have A, okay, B with X, okay. So I'm going to get B by itself. So I'm just going to get nickel, okay, plus A with X, magnesium nitrate. And magnesium, when it's in a compound like this, or when it's magnesium ion, has a 2+ charge. So that 2, that's why it stayed here. Okay, so it's the same idea for nickel nitrate. When you cross the charges, again, I'll just write it here, magnesium 2+, NO3-. Those charges crisscross, okay? Just to give you an idea of why that 2 stayed. Okay, so this is what's going on in these reactions. This is a single replacement reaction, and I'll just erase here just to write what's going on here. So magnesium and nickel are switching places. Okay, a single replacement reaction. Let's do another example. Okay, write the single replacement equation. So it's just telling us that it's a single replacement right off the bat for the reaction between solid and elemental calcium and an aqueous solution of hydrochloric acid. Okay, so we have elemental calcium, okay, plus hydrochloric acid, and go back to our section on naming acids to get what this is. Hydrochloric acid is HCl. Okay, so why don't you pause the video and try to write the single replacement reaction for this, okay? All right, so assuming you paused the video and you got the answer, let's do it. So here we go. So I'm going to write again, this is A, BX, okay? Gives me B plus AX. It's kind of like if you watch those old, my wife likes those old period dramas where like people are ballroom dancing and then somebody comes around and taps the person on the shoulder to switch partners in the ballroom dance. It's kind of what's going on here. All right, they're partners, BX, and A is coming along, kind of tapping B on the shoulder and saying to get out of here. It's my turn. So that's what's going on basically, if that helps at all. So probably not, but anyway, so B is by itself. All right, so this is going to be H2, because remember, hydrogen by itself, it's diatomic. Okay, so it has to be H2, so don't forget that, plus calcium chloride is what this compound is going to be, and it's going to be CaCl2, because calcium has a 2+ charge and chloride has a -1 charge. Okay, so that's what we get over here, and now we have to balance the equation, and it's pretty easy to do this. We have 2 hydrogen over here, 1 over here, so I put a 2 there. Okay, so that gives me 2 hydrogens on either side. That gives me 2 chlorides on either side, and that gives me 1 calcium on either side. So this equation is balanced. And again, just to write what's going on, okay, calcium's taking the hydrogen's place. Okay, so this is single replacement reactions. So here's a quick summary. It's an element, all right, as we've seen, like elemental calcium, plus an ionic compound or an acid. And the element basically takes the place of the other guy. So the one element that was by itself to start the reaction switches places here, okay? And so you end up again with an element plus an ionic compound. Okay, there's that switching of places for a single replacement reaction. Okay, well now the next thing that I mentioned is, what about a double replacement reaction? Well, it's kind of in the name, right? What is a double replacement reaction? So this is the example, I guess, with square dancing. I've never square danced, but my understanding is you change partners quite a bit in square dancing as you do it. Maybe I'm totally wrong. If anybody watching this video is a square dancing aficionado, you can let me know what's going on with square dancing. But my understanding is partners are switching all the time, okay? And like I said, maybe I'm totally wrong. But here, you start with, or let me give the definition first. It's ions of 2 reactants appear to change partners in a double replacement. So here we start with AX plus BY, and we end up with AY plus BX, okay? So they switched partners. And this is something we're going to talk about later, but often a solid precipitate is formed, okay, in these reactions. So that's something we're going to talk about later. But again, the ions are switching partners, okay, from these compounds. I have no idea if that has relevance to square dancing, but if it does, great. Okay, so let's just do some examples here, and I think it becomes clearer with examples. So zinc bromide and potassium carbonate solutions are combined. Write an equation for this reaction. So it doesn't tell us it's a double replacement reaction, but you see how we have 2 different compounds here? That should always be a hint to you that this is a double replacement reaction. We don't have an element by itself and a compound. That would be a single replacement reaction. So let's write down what we have here. So we have zinc bromide. Why am I doing that? Okay. Pull it together. All right, so zinc bromide, there we go. I was breaking all the rules. So zinc has a +2 charge, if you remember. Okay, again, from your chart on ions. And bromide anion has a -1 charge, so that's why we have this formula. Plus, okay, potassium carbonate, where carbonate has a 2- charge, potassium has a +1 charge. Okay, and so we want to write out this reaction. All right, so let me write out what we have here. So AX plus BY gives me, okay, AY plus BX, okay? Where again, you could think about it, if I just get another color real quick. Okay, so this is A, X, B, Y. Okay, so we just need to write that over here. Okay, so you're gonna, for now, okay, for elements, let's just ignore these subscripts on the bromine and the potassium. We're not gonna ignore the subscript here for the carbonate because the carbonate unit, the CO3, all of that together is a polyatomic anion. So it has to stick together. But this 2 on the bromide and the 2 on the potassium came from the charge of the zinc and the carbonate. Okay, so let's just ignore that for now as we switch over. You'll see what I mean in a second, hopefully. We'll do more examples together. Okay, so, so A with Y. So we're gonna get zinc carbonate. Okay, and zinc, right, has a 2+ charge. Carbonate has a 2- charge. So those charges cancel out. The molecule, or the formula unit, I should say, has a net neutral charge, okay? Zinc carbonate. Plus potassium bromide. Now, potassium has a +1 charge. Bromide anion has a 1- charge, right? So those charges also cancel out and the formula unit is net neutral. So that's what I was saying. These subscripts there, the 2, right, underneath of here and here, don't travel to the other side of the equation when we make potassium bromide because there's different charges for the ions involved there. So I need to redo those subscripts potentially. But I do need to balance the equation now because the equation is not balanced. As we just said, we have 2 bromides on the left side of the equation and 2 potassiums. So I could fix that by putting a coefficient 2 there. And now the equation, I believe, is balanced. Okay. So we don't balance the equation by changing the formula of things. We just use those coefficients. Okay, so this is an example of a double replacement reaction. Let's do another example. Silver chloride participates when a solution of sodium chloride and silver nitrate are combined. Okay, so this is something that's forming, right? But we're starting with sodium chloride and silver nitrate. So we're combining these 2 things together. So let's write our equation. So we have sodium chloride, NaCl, plus silver nitrate. Silver has a 1+ charge. Nitrate has a -1 charge. So they cancel out. The formula unit is net neutral already. Okay, and we're going to write what we have. Okay, again, this is AX, BY. I'm just separating them so you can get a better visualization on that. And I'm going to get AY, BX. Okay. If I write that out, again, they're switching partners. So A goes with Y. Sodium has a 1+ charge. Nitrate has a 1- charge. So that's that. And then silver chloride. Okay. And that was one of our products. Silver chloride precipitates. Okay. So I think it's already balanced. It is. So that's another example of a double replacement reaction. Okay. Again, we're just switching partners. So A is going over here. B is going over there. Okay. All right. So let's do one more example, I believe. Yes. So write an equation for the reaction between sulfuric acid and solid aluminum hydroxide. Okay. So we have to go back to naming acids, right, to write this down. But sulfuric acid is shown here. I'll just write it down. Okay. Plus aluminum hydroxide. All right. So why don't you pause the video, Do this one on your own, and then we'll go through it together. Okay, so again, I always like to just write down this guy. BY gives me AY, BX. Okay, it doesn't really matter what order you write them in. On the product side, I don't really care. You could have put BX, AY. It's the same thing. Okay, so let's do this. All right, so separate those guys so we could visualize a little bit better. Okay, so A is going with Y. Now, this 2, okay, did not come from the, isn't going to travel over, I should say, as we go through the reaction, because it came from the sulfate anion part of this compound, okay? It's a 2- and hydrogen is a plus charge, okay? So I'm just going to bring over the hydrogen by itself. He's free of the sulfate anion, if you will, okay? And he's going to be paired with hydroxide here. And again, that 3 doesn't travel over with the hydroxide because this is from the aluminum, which is a 3+ charge, okay? So this is just going to be our formula, HOH. Or totally fine to rewrite it as H2O, okay? It's water is going to be the product here. I'm just going to leave it as HOH so we could visualize better the AY part of this, that this was, or this came from the double replacement reaction, okay? But you could rewrite it as H2O, it's totally fine. And that's probably how you'll see it written in the homework and things like that. Okay, so plus aluminum sulfate, okay? Which is going to be shown here, okay? Because again, the aluminum has a 3+ charge, the sulfate anion has a 2- charge, so you need to make the whole formula unit net neutral. Okay, so now I need to balance this chemical equation, and let's see here. So on the one side of the equation, if I just start here, for example, I have 2 aluminum, okay? So if I put a 2 here, okay, that balances the aluminum, okay? Over here, I have 3 sulfate anions. So if I put a 3 here, that balances the sulfate ions, okay? And let's see here. So how many oxygens do I have on this side of the equation? So let me just erase a little bit. So hopefully you have that in your notes. I just need a little bit more room here to balance this equation. So, okay, let's see here. So sulfates are balanced, aluminums are balanced. You could also do this by elements, like sulfur is balanced. It's the same idea. So now let's see, how many hydrogens do I have on this side? So I have 6 there, okay, and 6 here. So I have 12 hydrogens, I believe it is. Over here, I only have 2 hydrogens. So I need a 6 in front of there. And I believe that might have balanced it, but let me just continue here. So oxygen, how many oxygen do I have on the side? Let me get out a calculator. So I have 3 times 4, so 12 oxygens here, plus 6, I have 18. Okay, and over here I have 3 times 4 plus 6, 18. Yep. So this equation is balanced. So those are examples of double replacement reactions. And remember to keep or be mindful of the charges of the cations and anions, make the new compounds, and then go back and balance your chemical equations, okay? And I'll just, for completeness sake, I have 2 aluminum 2 aluminum, 3 sulfur, 3 sulfur. Okay, so we have it there. All right, so that's it for single and double replacement reactions. Here's just a summary of double replacement reactions though. The solutions of 2 compounds, okay, each with positive and negative ions, are mixed together. They're switching partners, okay, as shown here. So we start out with AX and BY, we end up with AY and BX. And then 2 new compounds are formed, which may be a solid, water, an acid, or an aqueous ionic compound. We're going to talk more about how we tell what we're going to get in these reactions in a later chapter. All right, so that's it for single and double replacement reactions. You're going to get a ton of examples in the homework and in the lab report, I think that you're going to be doing, experiment 10, I believe it is. So make sure to do those. Reach out to me if you have any questions. And for the last part of chapter 8, we're going to be talking about reactions of hydrogen, carbon, oxygen compounds. So see you then.